Okay, welcome to the electronics class for September 29th. We have a bunch of stuff to talk about today. I have graded all of the midterm exams, and so now those of you that got them in late, you only got partial credit, and then there's one of you who didn't get it in at all, and it's now officially too late. So yeah, let's talk about the midterm exam, and then we'll talk about the homework, and we'll get into today's new stuff. Um, okay, so let's see, midterm exam. Let me share my screen here. All right, so I've got three different designs here that were submitted. This one here, I don't know if I don't want to name the names. If you want to speak up, if you recognize this as yours and you want to speak up, yeah, you're welcome to do it. Okay, so you can see,
I think that one's mine.
yeah, it is Henry, it is yours. Um, okay, so let's start the simulation. And when I push the button, you can see I get 20 milliamps. Same with this one, same with this one. Okay, and looks good. And then we come down to the bottom. Okay, I get 20 milliamps red, 20 milliamps blue, and 20 milliamps green. So, okay, looks to me like he did the job very well. Now, I want you to take note what happens if I turn on a couple buttons at the same time. So I'm gonna hold down the shift key and I'm gonna press the left button there. So the red one comes on. And now I'm gonna hold down the shift key again and hold them in the middle one. Okay, so we've got two buttons on right now. And so we had 20 milliamps with just one, and you can see we basically got 40 milliamps now, 39.9, same thing as 40, which is what you would expect. And then if I turn on the third button, so I'll hold that one down. Whoops, okay, sorry. Okay, click out of here. Okay, so you can see it goes up to almost 60 milliamps. Now it's not exactly 60 milliamps for reasons because this battery, the people who wrote the software here, they tried to simulate a real battery, and real batteries can't maintain their voltage if you pull too much current out of them too quickly. The voltage drops a little bit. So that's kudos to the people who did this simulation here. They did a really good job of simulating real batteries. Okay, but anyway, so I want you to notice that with Henry's circuit here, it works kind of the way that you would expect it would work. Okay, now let's look at this other circuit over here. You can see that this person decided to do it using only one resistor, which I think is very clever. And in fact, I gave this person bonus points for doing that. It's always a good idea to try and minimize the number of components. It's a good idea, but it does sometimes affect the circuit's behavior. All right, so let's take a look at this one. So if I click it, I get 20 milliamps. Click this one, I get 20 milliamps. And click this one, I get 20 milliamps. So far, it looks exactly like Henry's. Let's do the bottom one. Okay. So, yep. So far, the circuit is working exactly the same way that Henry's circuit is working. But now, let's try turning on multiples at the same time. So I'm going to hold down the shift key and click the left one. Okay, now when I click the one on the right here, with Henry's, it went up to pretty much 40 milliamps, 39.9. Okay, let's see if that happens now and by the way, does any student want to claim this one? If not, I want.
It's mine.
There were a couple here. Okay, so anyway, so here goes. I'm going to hold down the shift key, and look at that. It didn't go up to 40 milliamps. It only went up to 20.2 milliamps. Okay, and then if we click the third one, it goes up to 20.4 milliamps. So wow, this circuit is behaving very, very differently. Okay, and that's because of the way it is wired. And we're going to talk more about that in class today. So I don't want to go into too much detail. But let me just show you one more circuit that made me laugh when I looked at it. Okay, so here, this student decided they wanted to be different. Okay, so instead of using the 9-volt battery, they took 6 1.5 volt batteries, and they hooked them up in a way that makes it so that they still get the 9 volts just like before. Okay, so I thought that was a funny way to do it, but it's completely valid, 100% valid way to do it. So you'll notice that the way it's hooked up here, let me zoom in on this. Okay, so you see the electricity comes out the red one and goes into the black one of this guy. Comes out that red, goes black. So they're hooked up like this. So all of the electricity has to flow through all of the batteries. And so what happens here is the battery voltages add, just like resistor voltages add. So what this student has done is he's hooked up several batteries in series. So this thing about series connections and parallel connections doesn't just apply to resistors. It applies to other things as well. And here he's hooked it up with some batteries. Okay. And then I love the way that he routed his wires. You see this? Nice and neat routing of the wires. Makes it really easy to follow them. That's always a great way to do it. Now, for some reason that I don't understand, he decided he wasn't going to put this resistor on the breadboard. He's going to let it hang out here in space like that, which, hey, it's okay. I'm not really sure why he did it that way, but hey, it works. Can't argue with it. All right. And then just for grins here, let's start the simulation. Let's see if it works the way it's supposed to. So 20 milliamps, 20 milliamps, 20 milliamps. Okay, same down here, 20 milliamps, 20 milliamps, and 20 milliamps. Okay, now what if I turn on multiples? So let's turn on, hold down the shift key and hit this one. Now I'm going to hold down the shift key and hit the other one. And you can see this one is behaving the same way that the second one did. Okay, and by the way, that second one was actually Cadence one, but others of you may have done it in a similar way. Okay, and then if I turn on the third one, you can see. Okay, so clearly the fact that we've hooked this up using only one resistor has a big effect on the performance. But you don't notice it if you only use one resistor at a time. You definitely notice it, however, if you do multiple ones at a time. Okay, and now there's one other thing that I wanted to just mention. Take a look at this resistor. You see the color bands on the resistor? This is something that we have not yet talked about in class. And now is as good a time as any to start talking about it. Those color bands on that resistor are very important. Note what we've got. We've got, looks kind of an orangish color, and then there's a yellowish color, and then I think that one's maybe brown. And then we got the kind of a skinny band on the left there. Okay, so remember those colors, and let's go and let's compare them with this one. And you'll see we've got, it's orange, but this time it's green and then it's red. Okay, so definitely different colors there. So then last one here, let's come over to here. And again, you can see the orange, yellow, and then that one that's kind of, I think that's brown. Would you guys call that brown? Yeah. Okay, so why is it that some resistors have different colors than other resistors?
Isn't that just the way to show the resistance? How that the resistor has?
Yeah, that's exactly right. Resistors have a special color code on them that we haven't yet talked about, but I think this is probably a good time to do it. Let me pull in a resistor here and lay it over on its side. I like it better like that. And let's zoom in on it so we can see the colors. Okay, so if we look at this one, we see it's brown, black, and red. And when we click on it, you'll see that it's 1 kilo ohm. That's 1,000 ohms. Okay, what if I were to change that? What if I were to make it be, I don't know, 1.1 ohms? So let's try 1.1. Okay, did you see how the color changed there? Right. So if I go back to the one, okay, so the first and the third color bands stay the same, but the second color band changes. And instead of 1.1, let's make it 1.2. Interesting. Let's make it 1.3. Okay, 1.4. Okay, so that second digit, it tells you what the second band is. All right, so let's go through, and I want you guys to make a note here of, well, actually, you want to try, let's try the, well, now let's just finish what we started. Okay, so let's start off. So if the second digit there is a 0, notice it's black. So make a note. 0 corresponds to black. 1 corresponds to brown. 2 is red. 3 is orange. 4 is yellow. 5 is green. 6 is blue. 7 is violet. 8 is gray. And 9 is white. Okay, so remember those. Okay, now let's try the first one here. In fact, tell you what, rather than kiloohms, let's just make it be regular ohms. And let's start with, say, 100. Okay, so notice that the first color band here is now brown, which corresponded to the letter 1. The second digit is black, which corresponds to the letter 0. So far, so good. But the third one, that doesn't make sense, because the third one is a 0. And so 0 should be black, but that third one is not black. It's a different color. So clearly the third one works a different way than the first two do. Can anybody suggest a way? What's the deal with that third band? I know some of you know.
It's kiloohms, ohms, depicts like what unit of measurement they are.
Sort of, yes. Jasper has it. Jasper says that that third band tells you how many zeros to add after the 1 and the 0. Okay, so let's look at this one. Well, actually, first let's write down the colors. So let me turn on annotation here. Okay, so we got 0, 1, 2, 3, 4, 5, 6. I'm running out of space here. Let me move something. 7, 8, and 9. Okay, I just barely made it. Okay, so black, brown, red, orange, yellow, green, blue, violet, gray, and white. Okay, that's the color code. All right, and now if you want to know how I remembered that, how I was able to do that from memory, there's a they call it a mnemonic. It's a little kind of a memory trick to help. So the mnemonic that most books recommend that you use is bad boys race our young girls, but violet generally wins. Okay, so imagine you got a soapbox derby or whatever, maybe a bunch of little tricycles, whatever. And so the boys and the girls are having a race. Okay, and the boys, you know, they think they're going to win. So the boys race against our young girls, but violet generally wins the race. So bad boys race our young girls, but violet generally wins. That's the way to remember. Okay, so the first digit here is brown, so that means that it's a 1. Second digit is black, that means it's a 0. Now the third digit, the third band is what I should say. The third band is brown, which means 1. And so Jasper is telling us that that's how many zeros we should add. All right, so if we add 1 0, hey, look at that, 100, 100. Yep, it looks like Jasper's onto something here. Okay, let's try a couple more. Let me change the thing. Instead of 100 ohms, let's make it be 475 ohms. All right, notice the colors changed there. So now let's see if that works. Okay, so the first one is yellow. Okay, hang on a sec. Okay, first one is yellow, so that would be a 4. Second one is, that looks like kind of a violet color, I'm thinking. So that would be a 7. And the third one there.
That looks gray to me.
That looks
That looks
great.
real gray to me.
Great.
That's definitely gray.
That's great. Yeah.
Yeah.
It shouldn't be, because if it's a 7, it should be violet. Let's tell you what, let's change this to a 9.
Maybe it rounded up.
That's possible. Let me change it to a 9, and let's see how that changes the color. What? Okay, that makes no sense at all.
So I'm pretty sure it's rounding actually. Yeah.
Yeah.
Because if they rounded it, it would be 500. And
Oh,
that
they
makes
rounded
sense.
off. Oh, that's interesting. Okay. Yeah, that makes sense. Okay, so this is interesting. This is a bug that I didn't know about in the software. I never really looked before. Okay, so the color code that I'm teaching you is right. And if it doesn't match with what they've got in here, it is because of rounding, apparently. Okay. All right, so yeah, if they did that right, that one right there, that second one is, hang on a second. So that second one, it should be a 7, so 7 should be violet. So that color is not correct, but yeah, it's probably because of round off error. Okay, and then so the last one here, that's kind of a brown, right? So that means add 1, so we should add 1 0. So 470, and looks like they just rounded off. Okay, so anyway, keep in mind that the color codes that you see on the resistors, they're not just for looks. They are real. They help you know what color it is. But whenever we're using our software here, we don't really need that, because if we just click on the resistor, it'll tell us right here what the resistor is. So that's the best way to do it. But keep in mind that that is an option. So if we ever get back into face-to-face teaching and I pull out some real resistors, if you use the color code scheme that I just told you about, you can look at the resistor, and just by looking at the color bands, you can know what it is. Oh, the last thing we didn't talk about here on the color bands, we should do that. So this fourth band, the kind of a skinny band there, let me turn on annotation again. Okay, so this band right here, this has an entirely different purpose. This one is either going to be gold or it's going to be silver, and it tells you what is the tolerance on the resistor. Gold means that it's plus or minus 5%, and silver means that it's plus or minus 10%. Okay, so gold ones are slightly more expensive because they're made to a higher quality. So whatever these numbers say is the resistance may not be exactly equal to the resistance, but it should be within 5% if this is a gold band. But maybe if you buy some resistors from another company and they're not quite as careful with their quality control, instead of plus or minus 5%, they got plus or minus 10%. In that case, this band here won't be gold, it'll be silver. All right, so just keep that in mind. Not a big deal, especially if we're using the simulator here, because at any time on the simulator, we can just click on it and it'll tell us. So we don't need the color bands. Okay, so that's it for the midterm. I love the way that you guys connected the resistors here. You know, some people had diagonal wires. Other people decided they didn't want diagonal wires. They wanted all the wires to be nice and either perfectly horizontal or perfectly vertical. There was a tremendous amount of variety in how you did them. And then this one here, you know, I really liked this one here with the routing them, keeping them nice and clean like that. That isn't just a pretty picture. That will help you tremendously as you guys are making your circuits. Okay, if you can make them like the one that I just showed you, then after you make it and you try it out and you see it's not working quite right, and so you got to try and figure out which way is everything going so you can figure out where your mistake is. If you have your circuits routed nice and neat, like this one here, it's going to be so much easier to troubleshoot your circuits. So I absolutely highly, highly recommend that you guys do that. Okay, so before we move on, does anybody have any questions about the midterm? Not seeing or hearing any. Okay, so let's talk about last night's homework. Let's go back here to the course modules. So simple parallel circuits, that was the one that was due today. All right. And so let's see what we got. Okay, so we got 3 resistors connected in parallel with a 12-volt battery. We want to know what is the total resistance felt by the battery. Okay. Let's see. One of you guys want to do this? One of you want to talk us through how to come up with this?
All right, I guess I'm up.
Okay.
So, how you would find the total resistance is it's 1 divided by 1 over R1 plus R1 over R2 plus 1 over R3 and on and on and on.
Okay.
Oh,
All right, I like that. So R1 here is 350. Okay. So tell you what, let's make some room here so we can write them all. Okay, so 1 over 350 plus 1 over 470 plus 1 over 310, and we don't need to worry about plus, you know, on and on and on. Okay, so when I put that in my calculator, I get 1 divided by 350 plus 1 divided by 470 plus 1 divided by 310. Before I hit enter, let me look at it and make sure I didn't do anything silly, type any wrong numbers in there. Okay, I don't see any mistakes. Okay, so now when I hit enter, my calculator tells me 0.00821 and change. So is this our total?
no. So you got to go 1 divided by that number.
Okay, so this number here is 1 over our total. So if I want our total, then I have to do 1 divided by whatever that number is. Okay, so I could type 1 divided by into my calculator. If you've got a TI-83 or an 84, there's a button right here that says x to the -1. That is the same thing as doing 1 over it. So if I just hit an x to the -1, okay, it automatically, you probably can't see this very well, but it takes whatever was my last answer and raises it to the -1 power, which is the same thing as saying 1 divided by. Okay, so now I'm getting a number of 121.79. Let me share my screen here. Oops, whoa, everything went away when I did that. I hate it when it does it. Okay, so anyway, so it says it's 121.79. Okay, so if I type that into the box, we got a problem. Because what does this say here? Give your answer with only 2 significant figures or else it'll be marked wrong. So if I type this number into the box, well, technically, I mean, you know, that's the right number, right? Ah, but it's got too many sig figs. Okay, so how about, let's see. How about Isaiah? Can you tell me how many significant figures? Well, if I'm only allowed 2 significant figures, how should I write this number?
Well, if you're counting all the significant figures, 121.79 is wrong because it has 5 significant figures.
Good.
So what you need to do is you need to round up. So what you do is you need to round it to 120 because since the 0 on 120 isn't precise enough, it doesn't count as a significant figure. So you would take the 7 and you would round up to, no, you would take the 1 in 121 and you would round down to 120.
Okay, I like what he's saying. He's saying we got 2 choices. We could either round down to 120 or we could round up to 130, but we can't have anything after this column right here because then we'd have too many significant figures, all right? So, okay, let me just, okay. All right, so if our choices are 120 or 130, well, obviously, which one is this number closer to? It's closer to that one. So 120 is the number that we have to type into the box there. Otherwise, Canvas is going to mark it wrong. All righty. Okay, let's go to the next one. So how much current will the battery in there put out? Okay, so let's go back here, turn on annotation again. So the number on my calculator is 121.79. Actually, let me write that in a different place. I don't want to write it there. So the number that I wrote into the box was 120, but the number on my calculator was 121.79. So when I'm doing problem number 2, I need the current. So we know the current equals V over R. Do not use the rounded off number when you're trying to figure out what R is. You're going to run into problems like that, okay? So if this is your final answer, then yeah, round it off. But when we're doing problem number 2, this is not the final answer anymore. So what we need to do is we need to take the intermediate answer and plug that into here. All right, so what we're going to do is we're going to take 12 divided by this other number. So if I do 12 divided by my last answer there, okay, so I get 0.0985, okay, and 27 and a bunch of other digits, right? Okay, so if I'm only allowed 2 sig figs, am I going to round this down to 0.098 or am I going to round this up to 0.099? Which one of these is that guy closest to?
Why? I may be wrong, but I think it's 098.
Well,
maybe.
Look at the number after the 8. Okay, it's more than halfway in between the 8 and the 9.
Should be 99.
Yeah, we're going to have to round it up. Okay.
Oh, I thought the significant figure rule said like if the thing behind the 5 or something is even, you don't, or something like that.
There are some teachers that talk about the even odd thing, but in this case, even those teachers would agree that you have to round up. If it was 500, then there are some teachers that say that you round up sometimes and round down sometimes, but they don't have a really good argument for doing that. So in physics, we always just say if it's 5 or more, round up. And it's definitely more. This is not just 5. This is 527. So even the people that round one way one time and one way another time, they would even agree that we definitely have to round up. So our answer is 0.099, okay? But is that our final answer? Because if you come down here, you'll see that none of those answers are 0.0 anything. But one of the answers is 0.99, okay? Because 99 milliamps is the same thing as 0.099 amps. Okay, these two numbers are in fact the same. So you guys need to get really comfortable with converting between milliamps and amps and kilovolts and volts. You need to be really comfortable with that. All right. Let's move on to, oh, I guess that was it. All right, that was our last problem. Okay, I hope everybody is comfortable with how we did that. This is something that all of you need to be very, very good at. Any questions before I move on to today's stuff?
Can I resubmit? Wait, are you able to resubmit?
Well, the problem is I've just given you the answers, right? So
Oh, yeah, that's right.
what value is there in resubmitting?
Yeah.
So the answer to that one is no, I'm sorry, you can't resubmit. Now, you may have been talking to my physics students because they will tell you that I do allow my physics students to resubmit quizzes, but the difference is I don't go over the answers for my physics students, okay? So if they get it wrong, they have to figure out what they did wrong. Now, if you wanted to do it that way in this class, I could maybe be talked into doing it.
No.
Okay. All right. Okay, so let's go into today's stuff. All right. So today we're going to talk about what are called series/parallel circuits. What that means is we're going to deal with circuits where some of the components are connected in series, but other components in the same circuit are connected in parallel. Right? So when you go into Canvas to look at your homework tonight, you're going to see something that's going to look like this. And so it's going to say, so first read this section of the book and then read this section. Notice it says you can stop once you get to the part where they talk about SPICE, because this SPICE thing that they use is a computer program, which I think is really outdated. Yeah, maybe 15 or 20 years ago, it was a neat thing to use, but now there are so much better things out there. So yeah, once they start talking about SPICE, you can stop reading. Okay, so let's click on a couple of these and maybe see what's in there. Okay, so the first thing is just what is a series parallel circuit, and I've already told you what it is. It's a circuit. So what you see right here, that is a purely series circuit. And so how do you know it's a series circuit? Well, because there is only one loop. The current can only take one path. There's no place here where you get to a junction where the current says, okay, or I could go this way, or I could go that way. None of that. There is one path and only one path. All of the current that goes through this resistor has to also go through this one, has to go through this one, has to also go through the battery. So this is very definitely a series circuit, no question about that. All right, so now let's scroll down a little bit more. Okay, so what you're seeing now is a parallel circuit. Okay, so what makes it be a parallel circuit? Well, first off, you notice that we have these things that are called junctions. Okay, so when the electricity comes in here, let me switch to a fatter pen here. When the electricity comes here, you can see it's got a choice. It could go down this way or it could go that way. Okay, now that in and of itself doesn't make it a parallel circuit. That just makes it not be a series circuit. The thing that makes it be a parallel circuit is the fact that all of these resistors here are connected up to each other using one wire. The voltage is the same. So this is important to remember, and let me just click here so I can look you in the eye here. Okay. The important thing that you guys need to know is that if you have a wire, the voltage on that wire is the same as anywhere else on the wire up until it comes to something like a resistor. When you pass on the other side of a resistor, then the voltage might change. But as long as you've got 2 points on a wire that are connected together and there's no resistors or capacitors or transistors or thermistors or any other kind of thing in between them, if you just got bare wire connecting them, they will have the same voltage. And that is what makes this be a parallel circuit. Okay, so if you look at, so this side of the battery is connected by a bare wire to that one, and also connected by the same bare wire to that one. So that means that the voltage on the top side of these resistors is all the same. And then if you look at the bottom, you see the same thing is true on the bottom. The bottom sides of each resistor here, those are all connected up together with just a bare wire. So that means the voltage on the bottom is the same. And so if the top is the same and the bottom is the same, then the thing that I like to call delta V, which is defined as V top minus V bottom, okay, that's delta V. Delta V is the same for all three resistors. That is what makes a parallel circuit, okay? So keep that in mind. Okay, so now let's go with the a circuit that's a little bit more interesting. Okay, so here we have a circuit that's a combination, series and parallel. Okay, so I want someone to unmute themselves and tell me what are two resistors that you see that are connected in parallel with each other. So let me just, so R1 and R3, are they connected in parallel? How about R1 and R4, are they connected in parallel? What are two resistors that are connected in parallel?
R1 and R2.
R1 and R2. Don't say it with a question mark in your voice. Say it with an exclamation mark in your voice. R1 and R2. If you look at this wire here, you'll see the tops of R1 and R2 are connected together by a bare wire. Don't worry about the junction there. The junction doesn't mean anything. That's just, we've just got bare wire connecting these guys. And then we've also got bare wire connecting the bottoms. Okay, so R1 and R2 are definitely in parallel. Okay, R3 and R4 are also in parallel with each other, but not with the ones above. So the two on the bottom are in parallel with each other, separate from the two on top, who are in parallel with each other. Okay, so in your homework tonight, your job is going to be to fill in this table. So you see the table right here. I love this table. This table is a really wonderful tool. If you think in terms of this table, it will help you. Okay, so your job is to fill in all of the numbers that go inside this table. So that means for R1, you need to figure out what is the current that's flowing through R1 and what is the voltage across R1. Same thing for R2. What is the current? What is the voltage? Same thing for R3. Same thing for R4. And then once you have those, then you can figure out what the total current is and what the total ohms are. Or maybe it might be better to do it the other way around. Maybe it would be better to figure out what the total ohms are first and then figure out what the total current is, okay? So let's work through this circuit here and let's see if by working together, we can figure out all of those values, okay? So let me recommend that a good place to start would be to say, if we were to take this real circuit here and replace it with an imaginary circuit that just had one resistor right here and one resistor right here, okay, where this resistor is these two guys combined together, and this resistor is these two guys combined together. So if we do this right, then the battery would not be able to tell the difference. Because remember the example that I gave? I said the batteries don't have eyes, they can only feel. So this battery on the left here is trying to push the electricity out, and it's going to feel some resistance. So if we do our job right and find the right value for this resistor and the right value for this resistor, then this battery on the left is going to feel the exact same resistance that the battery on the real circuit over on the right would feel. Okay, so that's our job here, is to find out what are those values. Okay, so I want all of you guys to, let's start with the upper set. So I want you guys to take a minute. use the skills that you learned in last night's homework and tell me what value of resistor should I use for my upper one here so that this resistor has the same equivalent resistance of these two guys together. So I'll give you a minute or two. When you get the answer, what I'd like you to do is type it in the chat box, but don't type it to everybody. I want you to send me a private message so that other people can't see the answer. Okay, good. I got one already. Let's see if I get some more. I want everybody to type in an answer here. Okay, I've got two of them now. Now, the person that just sent me his, he used 3 sig figs. And the person who sent me the first one only used 1 sig fig. This brings up an interesting point. These numbers that we're calculating here, these are not going to be final answers. These are going to be intermediate answers. So using a couple extra sig figs is a good idea. So I actually like 3 sig figs on this. Even though our final answer is not, 3 sig figs is going to be too many for our final answer. For our intermediate answer, I like that many sig figs. Okay, so it looks like everybody that has answered so far has got the right answer. Sig figs are different, but basically it's the same answer for everybody. Okay, but I still have a couple of you have not yet responded. Those of you who haven't responded, I'm a little worried. Okay. All right, now one person just sent me an answer, but the answer they sent me was in amps. Yeah, we're looking for ohms here. We're not looking for amps here. All right. Okay, so, all right, let's see how we do this. Okay, so it looks like almost all of you got the right answer, but a few of you didn't. Okay, so we know that 1 over R total is equal to 1 over R1, which is going to be 100, plus 1 over R2, which is going to be 250. Okay, so when I put that into my calculator, 1 divided by 100 plus 1 divided by 250. Okay, so I get 0.00, nope, sorry, too many zeros. 0.014. And so now I'm going to ask the question that I've asked before, and I'm going to ask it again. Is that equal to R total? To which you guys should immediately reply, no. What is it? This is 1 over R total. So if I want to get R total, I have to take 1 divided by that. That will tell me what R total is. So when I do 1 divided by that, I get the same answer that you guys got. So let me clear some space over here. Okay. So 71.4. That's the same answer you guys got. Now, some of you rounded it off to 71, and I can see why you did that, but I like to carry a few extra sig figs because this is not our final answer. This is just an intermediate answer. Okay, so now you guys, if you haven't already started, go ahead. You know what I'm going to ask next, right? I want to do the next resistor now, next set of resistors. So if we look at just these lower resistors, these guys right here, I want you to do the same thing you just did. Send me a private message telling me what value of resistor should this guy over down here be in order for him to have the same equivalent resistance as these two guys put together. Okay, so I'm seeing one answer. Okay, oh good, I'm seeing 3 answers now. And the answers that I'm seeing are the same. Okay, good. All right, so there are some of you who are not typing stuff into the chat box. So I'm really worried that some of you. Okay, up until now, everybody has all agreed, but whoever just typed in that last one, you had a different number there. Oh my goodness, now, okay. So again, I don't want to name you by name, but one of you is still giving me the number of amps, Why are you talking about amps? We're talking about resistors here. I want to know what is the value of the resistor. I'm not asking how much current yet. Now, at some point, I will ask about how much current, but I'm not there yet. Right now, I just want to know the resistance. Okay, so it looks like almost everybody's agreed that it's 127 ohms. By the way, this is ohms up here too. Okay. Now, a few of you have different answers. So I can see one person here got 550. And like I said, one person got 142 amps. So just the fact that I'm seeing amps, that has me worried. One person has 125 and one person has 127. So I'm thinking maybe that's just round off error. So I don't want to take the time to do this when I did the last one. The majority of you are saying 127. So I'm going to think that the majority of you are probably right, even though that might not be the case. Okay, so now we're ready for our next step. So I want to take this semi-simplified circuit and I want to replace it with a super simplified circuit. I want to replace it with a circuit that only has one battery and one resistor. So what we're going to do now is we're going to take these two guys right here. We're going to combine them together. We're going to replace them with one battery, where this one battery is the equivalent of these two guys over here put together. Now, before we do that, we need to ask ourselves, how are those two guys hooked up? Are they hooked up in series or in parallel? So again, I like the idea of you guys typing into the chat box. That seems to work really well. So I want everybody to send me a private chat message telling me either series or parallel. And those of you that didn't respond before, I want to see everybody respond this time. Okay, so I've got 3 answers there. And there's 16 people in the class, so I want to see 16 answers. Okay. All right, looking good. Okay, looks like you guys are great. Oh, it was looking good up until now. So 2 of you said parallel. Everybody else said series. Okay, so let's talk about why this is series, because series is the right answer. So if you look at the electricity that comes out of the battery, and you see all of the electricity goes through this first resistor, right? And then whatever electricity comes out of that first resistor, all of that also has to go through the second resistor too. So in a case like this, when all of the resistor has to go through, or all of the current has to go through both resistors, that is not parallel, that is series. Okay, so when you have series connections, if you're doing resistors, that makes it really easy. All you have to do now is just add them together. Okay, so 71.4 plus 127. Okay, so then this, if I only go with 3 sig figs here, so I get 198 ohms. You guys agree? Okay, so this is our total. This tells me that if I use one resistor only, and I connect that one resistor up to the battery, and by the way, it has to be the same battery, so it's a 24-volt battery. Okay, so this 24-volt battery and this 24-volt battery, they can't see what's out there. They can only feel what's out there. And because we've done our job right, both batteries are going to feel the exact same amount of resistance. They would not be able to tell the difference between the real circuit on the left and our imaginary equivalent circuit. Let's use that word. Only let's spell it properly. Okay. So this is what I'm going to call the equivalent circuit. It has the equivalent resistance, okay, but it's only got one resistor in it. Okay, so make note of that. Okay, the total current is 120 or 198. And also, let's make note of the fact that this guy over here, the equivalent resistance of these two guys by themselves is 71.4. And then this guy down here, the equivalent resistance for all of them is 127. Let's keep those in mind here. I'm going to clear out our drawings here. Okay, so now if we look at our equivalent circuit with only one resistor and one battery, could we calculate what the current is? Oops, I didn't want to do that. Hang on a second there. Okay. Could we calculate how much current is flowing through that circuit? The answer to that question had better be yes. Okay, so I want you guys to do that right now. I want you to calculate how much current would be flowing through the equivalent circuit, knowing that the voltage on it is 24 and the resistance on it is 198 ohms. So I want you, everybody right now, calculate how much current would flow through that equivalent circuit. And I want you to send me the answer in a private chat message. Okay, I'm seeing one answer. I want to see 16 answers. Okay, good. All right, the answers that I'm seeing are basically the same. Some of you have converted it into milliamps. Some of you have left it in amps. One person has an answer that's very different from the other people. Okay, so it looks like everybody except for one is saying that the current is 121 milliamps. Now, some of you said 120, okay? But remember, I like to keep a couple extra sig figs. So even though 3 sig figs might be more significant figures than I'm going to be allowed in my final answer, then I still want to carry a couple extra sig figs and only put them only round off at the very, very end. So Isaiah, I see the public message. You just said your messages aren't going through. What do you mean by that? Try sending me a private message and I'll see if I get it. You know how to send a private message? Okay, yeah, I'm getting it, Isaiah. So I don't know why you say your messages aren't going through. I just got that test message you just sent me right now. Okay, so we are, though they appear gray for you. I don't know about that. Tell you what, let's worry about that later. Let's talk about electronics now. Okay, so now we know that the current flowing through here is 120 milliamps. That means that the current flowing up to here and the current flowing down here is 121 milliamps. Okay, but once it gets to here, then it gets interesting. Actually, let me switch to a different color here. So once it gets to this point, then it splits. And some of it goes this way and some of it goes that way. So the current through R1 is not going to be 120 milliamps. Well, current through R2 is not going to be 120 milliamps. Okay. But the two of them together will add up to be 121 milliamps. So now, if only, let me do my favorite thing here. Actually, if I stop sharing here, I'm afraid my notes are going to go away. I don't want my notes to go away. Okay, so let me just say, if only there was some way we could figure out what the current is through R1 and R2. Anybody got any ideas? How could we figure out what the current is that's flowing through R1 and R2?
Ohm's law.
Ohm's law. Could you be a little bit more specific? How would we use Ohm's law?
Solve for the current voltage over resistance.
Okay, I like where you're going, but let me just include the one thing that maybe you're thinking and you're just not saying. Let's go back to our intermediate equivalent circuit where we had a resistor here and we had a resistor here. And remember that the value on that upper resistor we decided was 71.4. And the value on the lower resistor we decided was 127. Okay, so could we figure out what is delta V across this resistor? So if I just wanted to know what is the voltage drop just across this one resistor, could I figure out what that is? Well, the answer to that is yes. We know that the current flowing through this resistor is 121 milliamps. Okay, now remember, that's not the real resistor. That resistor is just the equivalent of these two, but that's okay. If we use this equivalent resistor, and we know there's 121 milliamps flowing through it, and we know that it's 71.4 ohms, that means we can figure out what the voltage drop is across that resistor. Okay, so I'm sure you guys know what I'm going to do next. I want everybody to tell me, to do the math and tell me what is the voltage drop across this imaginary resistor here. Now my drawing is getting pretty bad. So while you guys do the math, I'll see if I can clean up my drawing a little bit here. Okay, so we know the value of the resistor. Ooh, oh, I hate it when I do that. I wish there was an undo on there. I go to draw things, and then I end up erasing. Okay, so we know that the value of this resistor is 71.4. We know the current flowing is 121 milliamps, which, by the way, is 0.0, no, I'm sorry. It's 0.121 amps. Remember, whenever we're using Ohm's law, we don't want to work in milliamps. We have to work in regular amps. Okay. So I'm not seeing any numbers in the chat box yet. Okay, now I'm
You're
seeing one
solving
number.
for the voltage across, right?
Yes, I'm solving for the voltage across that resistor. So hopefully you guys remember that V equals I times R. So I know what I is, I know what R is, okay? And I'm seeing I'm seeing a couple different numbers. The number I'm seeing the most is 8.64. Let me make sure if I agree that that's, so 0.121 times 71.4. Okay, so I get 8.64. Okay, good. All right. So that tells me that delta V here, boy, my picture is getting a little bit crowded again. Let me do a little cleanup again. Try not to clean up things I don't want to clean up. Okay, so delta V, that's the voltage just across this resistor from this point here to this point here. That voltage is 8.64. Okay, now that I know that, that is also the voltage across these guys. So if I were to hook up a voltmeter and I connect one lead right here and the other lead right here, and I connect that up to a voltmeter, that voltmeter is going to read 8.64 volts. And because these two wires are connected, or because these two resistors are connected by the one wire and this wire down here, the voltage across R1 is 8.64. The voltage across R2 is 8.64. Now I can calculate what the current is through R1. So I want you guys to do that. I want you to tell me what is the current that is flowing through R1. So I'm going to call that I1. So hopefully you guys know that that's whatever is the voltage across R1 divided by whatever is the resistance of R1. So we just got through saying that the voltage across I1 is 8.64, and we know that the value for R1 is 100. Okay, so I need to see some numbers in the chat box here. Guys, you don't even need a calculator for this. All you have to do is, if you're dividing by 100, all you have to do is move the decimal over 2 places. Okay, so yeah, 0.0864. That is the current, which, by the way, is the same as 86.4 milliamps. That is how much current is flowing through R1. Okay. Now I want you guys to tell me how much current is flowing through R2. Now, because they are hooked up in parallel, the voltage across R2 is going to be the same as the voltage across R1. So all we have to do is, so that means I2 is equal to delta V. Let me just clean up a bit here. For some reason, it doesn't want to let me. So delta V divided by the resistor, but this time it's not R1, this time it's R2. All right, so I'm seeing one number. I need to see a few more. Keep going. I'm only seeing 2 numbers so far. Come on, guys. We know that delta V is the same as it was before, so 8.64. Now R2 there is kind of hard to see. Maybe okay, there, if I do that, is that better? So R2 is 250. So whatever is 8.64 divided by 250, that's our answer. So now I'm starting to see, so it looks like everybody is saying is 34.6 milliamps. Okay, so 34.6 milliamps. Okay, good. Now, I like to do a little sanity test at this point. We know that the total current coming in was 121 milliamps. So that means if I take these two guys and I add them together, it better add up to be 121. If those numbers don't add up to be 121, that means physics is broke and we can all go home. Or it could mean that we made a mistake along the way. I mean, that sometimes happens too. But maybe this will be the time that physics is broke. So add those two numbers together and tell me, do they add up to 121?
Yes.
Oh, rats, that means physics isn't broke. Doggone, that means we can't go home. How disappointing. All right, you guys see how this works? Now, my clock is telling me that it's 3:30, so I don't want to go too long here. But I trust that you guys realize now that we could do the same thing that we did on the bottom. And so we can calculate what I3 is the same way and calculate what I4 is the same way. So I'm trusting that you guys can just follow the example that we did there. Okay. Now, just in case what we did didn't make sense to you, just in case maybe we went a little bit fast or something, if you read through the book, okay, if you read through this section right here, it doesn't tell you how to do it. But if you come down and click on this next one, which, by the way, remember in the assignment I gave you 2 links. So what you're seeing right now is the second link, okay? Analysis techniques for series parallel resistor circuits. So what they're going to tell you in here is basically exactly the same thing that I just did. Step number 1, step number 2, step number 3, all of these steps here, these are basically what I just did. So if you guys read through here, then it will help. And so I think that you see how they've replaced the 2 resistors with just one resistor here, and then the bottom 2 with just one there, okay? And then they replaced it with just one resistor that's the overall everything. So everything that I just did, they described it here. So if you had trouble understanding what I did, you just read the book, or you can always go back and just redo rewatch the video. Okay, so when you're done, you're going to see here is the quiz that's on Canvas. The circuit layout is exactly the same circuit layout that we just talked about. It's exactly the same. The only thing that's different is the numbers are different this time. Okay, but the process will be exactly the same. I actually feel guilty here. Personally, I think this is too easy. What I should do is I I should make it a little more interesting by switching up the resistors. But I figured, okay, I'll be nice to you this time.
Yes, please. I'm already kind of confused.
Okay. All right. So that's your assignment for tonight, is just solve that circuit that's on the quiz. But before you solve that one, I highly recommend that you go back and read the book and, follow through what they do and make sure you understand what they do, and then go into Canvas and take the quiz there. Okay. Are there any questions?
When you figure out the like the amount of voltage that goes across the first parallel resistors, do you subtract that from the total to find the second one, the second pair?
That's the easy way to do it, yes.
Okay.
There is another way that you could do it. Well, you could just repeat everything that we did for the upper resistors and do that same thing for the lower resistors. You could do it the exact same way, and guess what? You get the same answer either way. But what you just suggested, yes, that is certainly going to be the faster and easier way. So by all means, I'm all in favor of doing it the fast and easy way.
Okay, thank you.
Any other questions? Okay, not seeing any, not hearing any. Okay, so before you leave, I'm going to turn off the recording just in case some of you might have some questions you didn't want to ask because you knew it was being recorded. So here goes. I'm going to turn off the recording.